All right. Hey guys, so this will be lecture 4, Trusted Hardware. It'll just replace the in-person lecture because you guys are writing your test today. Good luck with that, by the way. Um, but yeah, so today we'll be discussing trusted hardware. I think this builds on the previous lectures in the sense that, in the prior lectures, we were discussing OS and VM isolation and software isolation, which protect us from a very particular kind of threat model. In the reading, actually, I think they put it quite well under section 2.2. You can see BitLocker, which is the sort of trusted hardware thing that we are covering. Hopefully, I don't have to explain it too much if you guys have gone through the reading. But BitLocker obviously cannot be a software-only technology, they say. Every software-only solution is vulnerable to software-only attacks. So here they're specifying effectively their threat model, right? The threat model that they are concerned with is effectively they want to be able to cover all software only attacks, including ones that relate to the, if you like, the theft of hardware. So, like if I steal your laptop, for example, I can boot into another operating system, like I can connect a USB with like a USB stick with Linux on it, for example. I can boot into that Linux bootable, and I effectively then have sudo access, and I can access your drive directly, right? How would a software system protect against an attack like that? And the answer is it can't really, right? If we're in a server or data center context, which BitLocker, by the way, is made by Microsoft, so it's like, of course, they deal with a lot of like server and data center type setups. In a setup like that, if someone gets access to your data center and they steal a hard drive, they can almost certainly read that hard drive. They could use a tool like I have one here actually. I don't use it for nefarious things. I mostly just use it to clone disks to each other. So effectively this, you can put HDD or SDD here and an HDD or SDD here, and it just clones the one from the other, all the data. But what you can also do with this is you can plug an HDD in, and then I can connect it to my computer, and I can just read any data off of that drive as if it's a USB stick. So if I stole your laptop, unscrew your HDD, if assuming your drive is not encrypted, like you're not using something like BitLocker, then using a simple thing like this, you can get all of the person's data off of it. And then there are other situations where this type of hardware protection is used quite regularly. One of them is in what's called high bandwidth digital content protection. I can give you guys a quick example of how that works. Actually, let me keep my video big here. So I am sharing this screen over here. I'm sharing from my tablet to here. But you can see on my tablet, there's a video playing here, right? So like you can see there's a video clearly playing. But if I sharing this screen through this USB-C cable to my laptop, you can see you actually can't see the video. So it's a pretty, actually, let me just see if I change the size here. Okay, so you can see video playing here, but on the actual laptop screen, it's just a black empty screen. That's because this USB-C connector here is protected at a hardware level. It has some DRM protection through a system called high bandwidth digital content protection, I think HDCP. We won't be discussing HDCP too much, but I do want you guys to know that that falls under this set of trusted hardware. In particular, the trusted hardware we will be discussing is what's called a TPM, which again, in the reading, you would have seen something of. So there's this TPM security chip over, you can see it over here. This stands for Trusted Platform Module. it maintains a bunch of registers called platform configuration registers, or PCRs, PCRs for short. So this is effectively a chip that's on the motherboard to allow for a certain kind of trusted hardware protection. There are quite a few different types, which like we will go through. Like I think we've already gone through one of them. HTCP is another type, but this TPM fulfills something called measured boot and also allows for disk encryption in the way that BitLocker required. Cool. So, all right, and these effectively what the TPM is allowing us to do in the context within the context of BitLocker and what BitLocker wanted to do. I think we've discussed quite a lot before this idea of the trusted computing base, and we want to minimize the size of our TCB of the trusted computing base. And in the case of BitLocker, you know, we might have a network which is untrusted. We might have a corrupt application which is untrusted. But typically the disk would fall under what we consider trusted, like we can safely store things on the disk and we can assume they're confidential. BitLocker is no longer making that assumption. The only things BitLocker trusts is the CPU and ROM. It doesn't trust the disk, right? It wants everything saved on the disk to be encrypted, encrypted at rest. Okay, so yeah, the other thing is when we load things from the disk to run them, like when we load the OS kernel or whatever from the disk, we want to verify that it is what we expect. I mean, in some cases, we want to verify that it is what we expect. In other cases, we just want to measure what was run. So this is a difference between something called measured boot. There's maybe three categories here: measured boot, secure boot, and verified boot. They're all slightly different, and yeah, we'll go into those differences. But effectively, these differ in what we're willing to load from disk. But yeah, effectively, we want to be able to trust the CPU and memory, or in particular ROM. Okay, so yeah, like I think, so the attacks that we're trying to protect against here are like a laptop or drive theft attack, right? Like if I steal your laptop, currently, if it's not encrypted, I can probably read all of the data off of it, right? We want to be able to protect against that. And the truth is, there's very few ways to do this in a software only way. In fact, I guess there's almost none. Right? The only way to do this is if you have some kind of trusted hardware that's doing the encryption. And I mean, there could be one other way, which would be like perhaps the encrypting with the user passphrase, but we'll see why BitLocker maybe didn't want to do that. Okay, so the way that we achieve this, right, is when saving things to the disk, we need to encrypt the data on the disk. And then when reading from the disk, we decrypt it and then give it to the user. So that means that if an attacker steals the drive, if they try to read the data that's on the drive, they will be unable to read it unless they have the decryption key. This raises an obvious question: is where is the key, or even what is the key? So I think there are a few separate candidates that we could have. One obvious one, and again, if you read through the BitLocker paper, they address why they didn't use any of these. But one obvious candidate might be, well, we could use the user password, right? So let's say you could, like, if my computer is locked, then my entire drive is in an encrypted state, say. And until I type my user password here, you are not able to see any of the data on my drive. So as soon as I type that password, then that password is used as the encryption key for all of the data on the drive. There are a few issues with this. A massive one for why Windows wouldn't do this is the question of, let's say we've got our drive, and we have our drive over here. If this drive is encrypted, the whole thing with my user password, what happens when I forget, if I forget my user password? The risk is just far too high, right? You would effectively lose all of the data on the drive. So this was eliminated as a candidate for BitLocker, primarily for this reason. Um, like a user passphrase has pretty high risk, just because it's very easy for a user to just forget their password and then they lose all of their data on their laptop forever. That's like, of course, unacceptable. So another one that they discuss here is perhaps you could store the password on a separate USB key. So you can imagine like my drive is encrypted and I have this special USB, and in order to read any of the data on my drive, I have to connect the USB to the computer, and then it uses the key on the USB to decrypt the drive. Of course, this doesn't actually solve the problem, because if the person can steal the laptop, surely they can steal the USB, right? So it's like, this is not really achieving much. Like if they steal both, if your laptop is on, like if your laptop is on in this locked state when they steal it, it's highly likely that you were using your laptop, and so the USB would probably be connected. And of course, the question still remains, well, what if you lose this USB? There's no way to recover what's on the drive. And so the solution that they arrived at is having some kind of trusted hardware chip. And yeah, the chip that they use is called the TPM. The TPM effectively is doing something called a measured boot. And it works with a few like very simple primitives, one of them being extend. Because we covered a lot of the stuff in the cryptography course last semester, like I'm sure you guys saw the title of this paper has AES CBC, right? AES in cipher block chaining mode. So hopefully you guys all know what that is. You could also see this word diffuser. If you remember when we discussed confusion and diffusion in first semester cryptography, yeah, hopefully a lot of these words are ringing some bells for you. But yeah, effectively this extend function is a hash function. Works a lot like Merkle trees do. If you remember the Bitcoin project, like that Merkle root type of concept is quite similar to how the hashing works for the extend function. But we'll go through a quick demo of that. But you can see what this extend function does is it sets a platform configuration register, the PCR, to the hash of its old value and a supplied data string. And this allows us to do something called a measured boot. So before we go on, I do just want to mention what the difference between like a secure boot, a measured boot, and a verified boot are. Because yeah, it's a pretty big difference in how these things work. So just as okay, so effectively, when we run through our boot processor, let's just say, we've got like our BIOS. Into maybe our bootloader, into maybe the OS kernel. Okay, okay, sorry about that, guys. So yeah, okay, we've got our BIOS bootloader into OS kernel. So effectively we've got this concept of a measured boot. The measured boot just wants to document what versions of software were running and what was run in order. So the measured boot might start with a PCR, right? A platform configuration register, a pretty well-named thing if you think about it, like what it actually does. And initially, let's say when we boot up, the computer knows like, okay, we need to reset the PCR, okay, so that it's just a bunch of zeros, okay, a bunch of zeros. And then we are going to update the PCR. We'll update the PCR, and we're going to set it to the hash of its current value, which will just be a bunch of zeros because we just reset it, and let's say the entire bootloader. And this would be the actual code of the bootloader hashed. Okay, cool. And that'll obviously give us some unique hash. And of course, hopefully you guys remember what the hash function does in cryptography. One, you'll remember that one requirement for a lot of hash functions is that they are extremely fast, and it's because they're hashing a lot, right? So they need to run very quickly, and they are very collision resistant, right? So if you change the bootloader slightly, we'll end up with a totally different hash. Okay, and so there's no, like it. If the bootloader is modified at all, the hash will change. So if it's a version 1 of the bootloader or a hacked version of the bootloader, it would produce a different hash. Remember, the measured boots won't necessarily block anything from happening. It's just logging what's happening. Okay. Then likewise, we might say, okay, well, we've after the bootloader run, we took the hash of the PCR with the next thing that ran, which was the entire OS kernel, for example. Okay. And then that updated the PCR again. And so now it's like this version of the bootloader and this version of the OS kernel gives us some unique hash. And what BitLocker does, I think just as an introduction, is uses this hash as the key. Okay. So this is effectively how a measured boot process works. You can, like, ignoring the key thing. The measured boot is just saying we ran these things in order. And so we get this hash at the end, which sort of uniquely specifies what things were run for the boot process to arrive in its current state. Okay, so it's just measuring. Notice it's not saying like, "Ooh, the bootloader is corrupt. I'm not loading it," or "Oh, this OS kernel is not what I'm expecting. I'm not running this OS. I was expecting to run Linux, and you want to run Windows, so we're forbidding the run." The measured boot is not doing any of that, right? Alternatively, there's something called a secured boot, which most PCs currently use. At the beginning of secured boots or secure boots, a lot of PCs weren't using this yet, simply because there's so much different software being run. But now there's something called a shim that Microsoft maintains, which is effectively just a way for like distributions of Linux, but also Windows and stuff, to get a unique signature. And the BIOS or UEFI will check that the signature of the system about to be run, which if you guys recall, that I could just say, like, if we hash the bootloader, right? Like, let's say we're Microsoft, we're releasing a new version of this bootloader, or we're a hardware provider and we're releasing some new system for like a motherboard or whatever. We will sign. We would effectively sign with this hash. Okay. Just a quick reminder of how digital signatures work. And so this signature we will distribute along with the system, right? So it's like you get the bootloader, and a signature linked to that bootloader. And then, of course, you can verify locally that this bootloader matches this signature. And you can save this signature in a trusted place like ROM, where and just say, okay, this signature we trust, and so we are willing to run this bootloader. We verified that this bootloader was actually produced by Intel or whoever said that they produced it. Okay, so yeah, this is how secure boot works, where it will actually not run the bootloader if the signature doesn't match. Okay. Then there's another version of this, an even stricter version called verified boot, which is effectively only used by OEMs, like original manufacturers. I think it's original equipment manufacturer, an OEM, like Android or Apple, where they own the hardware and the software that's running on the system. Various Android providers, I should say, like Samsung or Google. And they are effectively even stricter than Secure Boot. Like Secure Boot might verify that the bootloader is signed correctly, and that the OS kernel is signed correctly, and then just let you go on about your day. Verified boot will verify far more software than that, not just the bootloader and OS kernel, as well as like even apps will be checked that they were signed by the actual Android store that said that they produced the app, rather than you having some corrupted version that's just claiming to be YouTube. It will verify that this YouTube signature is actually valid, right, against the Google Play Store or whatever. Okay, so I think I think so. Primarily, what we're covering here is measured boot. But I wanted you guys to know about these alternatives. I think quite an interesting one to read about is just the Android verified boot. Of course, app verification is a later step. This is during the boot process. So like that YouTube example wouldn't apply during the boot process, of course. But a similar thing where like these OEMs can verify that everything is signed as opposed to just the bootloader and the OS kernel. And that again, opposed to measured boot, which is actually not verifying anything. It's just measuring it, right? Just keeping track of what happened. But even just the step of keeping track can be quite beneficial. Okay, cool. So yeah, just move on to here. So measured boot is simply recording what ran. So we've like this. So what forms our trusted computing base in this concept of a measured boot is ROM, the CPU, and the TPM, right? The trusted platform module. So that's now our trusted computing base. And so most of what we'll be discussing from now is how this TPM works. So the TPM has a few primitives, effectively just three. I guess it's more like four. So there's the things we have to understand for the TPM. It has an extend function, which I think we already sort of discussed over here, where we extend with whatever is running currently, and then we can extend again, and it forms this kind of tree of hashes, or like a list of hashes that occurred in order. But the last hash is deterministically linked to all of the previous ones, right? We've got extend, we've got seal, which this is effectively encrypt, encrypt, and we've got unseal, which is effectively decrypt. Okay. Then the other primitive I'd say is reset, but this hardly requires learning, right? Reset just takes the PCR and sets it all to 0. Okay. Seal takes the current value of the PCR, and encrypts something with it using that current PCR register as the key. Unseal obviously takes the current PCR register and tries to decrypt something. Okay. So this I think describes it quite well. So the extend takes the PCR register, right, and updates it with the hash of its current value. Concatenated with whatever we're measuring. For example, the bootloader, or whatever, or the OS kernel, or an app that you're running, whatever. You can put whatever you want there. We will go through a quick demo of this. Seal effectively produces a blob, like a file, an artifact, that is encrypted using the current value of the PCR. So it just takes in the data and the value of the PCR. So you can notice here that we do say expected PCR here because there is something that we'll just have to discuss about this. And then decryption effectively will give you back the original data. So you can see seal is taking in this data, unseal will give you back this data. It will take the current configuration of the TPM and the blob, the encrypted file. And if the PCR value that you specified during encryption, this expected PCR, if that matches the current PCR register, then it will give you back the data. Otherwise, it will panic. Okay. Okay, cool. So yeah, that's effectively how this works. So the key is released only to the expected machine state. Okay, so I do want to just describe some other things from the paper. Cool. So effectively what this allows us to do, like why do we want to do things this way? So of course we discussed before that now because we have this TPM and it's effectively storing the key in this hash of the current machine state, we actually don't need to store the key anywhere in data. And so we can effectively guarantee that our ciphertext is the same value as the same length as our plain text. And so, you know, when we produce I guess to just make this clear, this should be maybe duplicated. Yeah, we can effectively guarantee that they are the same length. One is just like an encrypted version of it. And this doesn't require any action by the user, right? And it will be very fast because we're using AES. So yeah, I think like a lot of the alternative ways of performing this type of encryption would require us to store a key somewhere, which would just invalidate a lot of what's going on, right? Because the user would not want to, let's say they have 255 gigs or whatever, like 255 gigs of unencrypted data. If you were like, hey, do you want to switch on BitLocker or do you want to encrypt your drive? But by the way, you would need 300 gigs. They in like the encrypted state, the user would say no, right? They need this guarantee that no extra space on their drive will be used up by the encryption. They don't have to remember a password. It's all just handled by the TPM. Okay, and by BitLocker, of course. So okay, I do want to discuss the paper a little bit more. Just some of the like findings that they went through. So yeah, like I think one interesting thing, if we think back to the cryptographic services that we were discussing last semester, right? Confidentiality and authentication, non-repudiation, and data integrity. BitLocker is not guaranteeing authentication, right? So that's just what they're saying here. All they care about is that the information on the drive is confidential. Okay. They're not 100% interested in the fact that they're not super concerned about the idea that a certain sector might have been tampered with. Because of course, if we were trying to provide authentication in this kind of context, right? Let's say we've got sector 1 here and we are getting an encrypted version of sector 1, right? Let's call it C1. How we might typically do this is we would store C1 with like a MAC or something, right? Some kind of authentication code, right? To verify that C1 has not been tampered with. And this could provide data integrity and authentication. But what the major issue with this is it would take up more space, right? Which is a deal breaker. And so they don't really care about this. But what they do have is a kind of poor man's authentication by the fact that if you did mess with C1, right, like if you tried to change C1 in some way that when we decrypt it, you have affected S1, because of the amount of diffusion that is happening, and that's why diffusion was such an important consideration, right? They designed this custom elephant diffuser. Why diffusion was such an important consideration is because they want any change in S1 and vice versa, any change in C1, to cause a large number of random changes in the original or in the ciphertext, right? So diffusion was a very important consideration for them. Okay. The other issue is, like you saw at the start of the paper, they use AES in cipher block chaining mode, CBC mode. CBC mode, you guys might remember, requires an IV, right? Some kind of nonce. And we need this because obviously if we were encrypting just in electronic codebook mode, right, ECB mode, then it's vulnerable to replay attacks, right? Like if sector 2 and sector 3, if these various parts of the drive contain similar data, they need to be encrypted differently. And so what they actually do is the IV is the sector number. So, you know, like quite a clever way of resolving this issue. And the diffuser also depends on the sector number. It's sort of randomized for the sector number. So like effectively what they're allowing to happen is it means we don't need to store an IV and we don't have to store any kind of nonce anywhere for the diffuser to work. These are both handled by the CPU in like a volatile way. Okay. So they don't have to be stored to disk, which means that we can just encrypt the sectors and we can be sure that no extra space is being used up. I do want to just mention one thing on the paper as well. So sorry, that's the WebAssembly one. The BitLocker, this BitLocker paper does mention, so they use AES CBC with the elephant diffuser. And when this was written in 2006, that is what they did. This was actually stopped in Windows 8. So yeah, this was stopped in Windows 8. And now BitLocker uses something called AES, I think it's XTS, if I recall. Let's just see, AES, yes, AES XTS. And effectively the requirements of AES XTS is one, it provides a lot of diffusion. So it allows them to replace this elephant diffuser. So just a lot of diffusion, because diffusion was an important thing because we require what's called, and they do mention it in the paper, poor man's authentication is how they refer to it, which diffusion is very important for allowing for poor man's authentication. And it also guarantees that the plain text length is equal to the ciphertext length. Okay, but you know, I think all of these, we didn't cover AES XTS in semester 1. Maybe we could cover it eventually, but it's very similar to, it relies on this tweak value, and that's basically based on, we discussed like that concept of Indianness, like little Indian and big Indian. It generates this tweak value, and it acts as a kind of nonce. But yeah, most of these alternative AES forms, I'm sure like these will look pretty familiar to you, like based on learning AES CBC and EBC and AES counter mode. Like they're all sort of you know, like diagrammatically represented like this. Cool. So yeah. So the paper is a little bit out of date in the sense that this diffusers section, like that I did quite like, they go through a bunch of alternative ciphers, like why did they choose AES in CBC mode? Like they couldn't use stream ciphers. Why couldn't they use stream ciphers? I think we know that from last semester, right? Stream ciphers don't provide much diffusion, and so they're ineffective for poor man's authentication. They considered bear and lion, but they were too slow. They considered another one called beast, but it was also had poor diffusion properties in their tests. They considered one called vil, but it was patented, so pretty untested. They considered mercy. They considered LRW. So but it had too small of a block size. So it's quite cool. They go through all of these different ones that they tested and why they failed. And so they settled on using AES CBC, but they felt that AES CBC didn't provide efficient diffusion. And so they created a diffuser called the elephant diffuser, and added it to achieve like the poor man's authentication standards that they want. But yeah, I just wanted to mention at the first bit, they do also mention Indianness here, right? So they use little Indian, least significant byte first encoding. But I think do go through this section on how their diffuser works, but just note that this elephant diffuser is no longer actually used. It's a very simple one to understand though. If you just read through the section, like if you have any questions, you're welcome to ask, but it's a very simple diffuser to understand. But do know that this diffuser stopped being used in Windows 8, and they now just use AES, right? AES in XTS mode. Cool. Okay, I did just want to mention as well. Yeah, a lot of the discussion here is on the attack model. I liked, they do use some terminology that you guys should already be familiar with, like chosen plaintext and ciphertext attacks. So here they do mention like this requirement of a kind of diffusion, right? Like effectively any minor plaintext change should replace a lot of the ciphertext in a sector, right? So one minor change in the plaintext should affect large portions of the ciphertext. If you guys recall, that is the definition almost of diffusion. Cool. Yeah, so I think that covers most of the paper. I think the best way to learn about TPM is to just get hands-on with it. So I think we can just do a quick demo of it, and then hopefully you'll understand how it works. And yeah, maybe we can end a little bit early. Let me just see how long have we been going? 38 minutes. Yeah, I think a pretty good time. Cool. So my system here does have a TPM installed. They're like, again, there are those 4 core primitives which I want you guys to know. But they're obviously when using it practically, there are quite a lot of steps just because nothing is ever perfectly simple. It does require sudo permissions to use, of course. The trusted platform module would. So let me just show you here. Cool. So what I ran here, so my system does have a trusted platform module in. Most modern computers would have one. I think there was quite a big controversy. I think it was around the TPM, that a lot of modern Windows systems, again, I don't really use Windows too much, but I think Windows 11 actually requires a TPM or something. And so a lot of older systems actually can't run it. Yeah, so effectively, so first we're just running this read, PCR read, which is just saying, I take all of the current platform configuration registers, and you can see my system has, I guess, 23 of them. My TPM module has 23 of them, or my TPM chip, and just tell me what their current values are. So you can see that there's a bank of SHA-1 registers, which mine is empty, I guess. So maybe this is just, I don't know why it's there. And most of them use SHA-256. I think it's fantastic. We don't have to go over too much. That's just the hashing algorithm that these were built with. Okay. So a lot of these will be used for specific things, I assume. I'm not sure. A lot of this is just a measured boot process. My drive is not encrypted, so I assume we can overwrite any of these. But we'll just pick one, right? So you can see they've arrived at specific states. So maybe like the current states of 16 is this. It's got like a whatever hash value there, SHA-256 hash value. And so we can actually reset it. So we can just say TPM2 reset 16. And then if I read it again, you can see 16 is now all zeros, right? So it went from being this other value over here to being all zeros. Okay. So then so that was the first primitive, right? We were saying like there's reset, there's extend, and there's seal and unseal. So hopefully you guys understand the one primitive now of how this works, right? You guys understand reset, right? Over here. Okay. So now let's pretend we were going through a normal boot process. So in like a normal boot process, maybe we would have something like a bootloader. Okay. And of course, this would be some code. It might be a bootloader written in C. It might have like include standard IO or whatever. I don't know. Been a while since I wrote any C code, but like let's say we've got our whole bootloader and we just pass it through SHA-256, right? Like SHA-256 sum. Okay, and it gives us this value. Okay. So we've got a hash of our bootloader. Okay. Then effectively, each of these registers is storing a portion of our current platform configuration. So obviously the bootloader we're running is a part of our platform configuration. Let's say we want to store that at 16. So to update, we run the extend command, right? So here's a PCR extend. So the settings for it are about what you would expect. So we've got sudo tpm2 underscore PCR extend. That's just, obviously this is just the command for extend. Then we're saying we're extending register 16 under the SHA-256 bank. Obviously we're not using the SHA-1 bank because we use 256 sum, and we're putting this value, like the value of this bootloader here, right? So there we go, we just extended it. And then now if we do a PCR read, it should be some other value. So you can see it's got this 30097, okay. I think we can just read 16, okay, or do we have to say 256? Or SHA-256, maybe SHA-256. What do we do? SHA-256 16. Okay, there we go. So now we're just reading just that register rather than reading all of them. Okay, but hopefully you guys see this is nothing special. It's just only showing us register 16 in the SHA-256 bank. Okay, then the way that TPM2 works, of course, it can't just like the core primitives are the same. So you now know reset, you know extend, right? We just hashed the current value with this other value. Before I can show you seal, there are a bunch of other things that you have to do, unfortunately. So how it represents stuff is a kind of tree. So like there's, I think they call it like an owner or a parent or something. And so under this owner, you have a specific context. So it's like, owner context, which we will just use the primary context. And then you have a certain policy under that context, and you can use that policy to seal certain things. I mean, of course, what matters here is the sealing. It doesn't matter how TPM2 represents it really, but this is how TPM2 represents it. So just in the demo, just beware there's some other commands that are not like super important, okay? So we can first start by creating a primary, tpm2 underscore create. Sorry, I'm just going through my history here. So we're creating a primary context, right? We're saying that the owner is owner, and this is the name of the context, okay? So, I mean, it doesn't really matter. All that matters is this is generating a file over here, this primary context file, and it has a bunch of metadata about, stuff like what encryption schemes are being used, SHA-256 hashing, like, how many bits it is, like it's just, how TPM2 on Linux is implemented. I think, for you guys, that's not super important. And then what is important is a policy. So again, like you could do this without creating a policy. It's just that TPM2 supports some different ways of doing things. So let's just keep this one simple. So we're saying create a policy. We want our policy to be based on the value of a PCR register because the TPM module can encrypt things or seal things in some other ways, but we're saying that this policy is specifically based on just the context of the register because that's the one we care about, sealing based on the value of the register. We link this -L to a specific register, which we're using register 16, and we're just outputting this policy in a specific file, which is just a .dat file, okay? So this just creates that policy. So you can see it just created policy.dat. And all this policy says is anything encrypted under this policy must match, to decrypt it, the value of the PCR register 16 must be whatever value it was at the time of encryption, right? So that's all this is saying, okay? Cool. And then now that we have a policy and a we have the policy and we have the context, we can now actually do the encryption, which is create. We do create. Of course, we need a secret to encrypt, right? So let's say we have our file image, our entire file image .txt, and on our file image, there's a super secret documents, right? A super secret documents. So I just created this file image.txt file, and in the txt file, it just says super secret document, okay? And we want to encrypt this, okay? And to do that, we can use this tpm2 underscore create, create a sealed document. What do we want to encrypt? So the input, that's -I. The input to this will be this file image.txt, right? We are creating, so let me maybe zoom out a little bit so you guys can see a little the whole thing. So tpm2 create, we've got the context that we're sealing this under because the policy exists under that context or whatever. That's just a detail about how tpm2 does it. We've got some public metadata about what's being encrypted. I don't know what this might be, like the time it was encrypted, whatever important things, metadata stuff. And then we've got the private part of it, which is the actual encrypted documents. And then, the policy that we're encrypting this under. So we remember that this policy specifies register 16. Hypothetically, you could implement this differently without a policy, right? And then the actual file, the input that we want encrypted. Okay, so we can run that. Cool, and so there we go. It's encrypted. And then now so again, unsealing has also, unfortunately, some steps. So before you unseal, you have to load. So there is this command unseal, okay? But in order to unseal something, you have to load it first. So we can just first do a tpm2 underscore load, okay? So here we're saying tpm2 load. We want to load from whatever context we're in. We're loading this public portion of the seal, like the metadata of the sealed documents, the private portion, and we're loading it into this sealed context, this blob that we'll then unseal. Okay, so this gave us this sealed blob still, and then now we can unseal this blob. Okay. So we want to unseal the sealed thing. using the value that is currently in the register. Obviously, we haven't changed the register, so we haven't extended the register, and so it says super secret documents, right? And of course, I can delete file image.txt, right? And just so you guys see, and you can see, so it's just using this encrypted version of the documents, and like the context of sealed will be, difficult, it's not really human readable at all, as you can see. It's just some binary whatever, gobbledygook. But when we unseal it using this register, it works. Of course, if we change the value that's at this register, it should fail, right? So if you guys recall, when we were running PCR read over here, this is the current value of the register 16. What if we extend it again? Like, let's say, after the bootloader, we added the OS kernel. Okay, so we wanted this thing that we just encrypted to be available to the bootloader, but we don't want it to be available to the operating system, for example. So we can extend register 16, right? So now the value of register 16 is this new thing, AE blah, 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 right? Because we just extended it again. Of course, I could have extended it with a different value, but hopefully you guys understand that for the purpose of this demo, that doesn't really matter what value would be here. But now if I try to run unseal, it should panic, right? It violates the policy. You see, it's like warning, received TPM error code, something, policy check failed. So this policy check failed. The value of the PCR register didn't match what was specified in this metadata or whatever, wherever it's specified. We weren't able to encrypt. The key was wrong. Okay. Of course, now if I reset, let's say we were going back through our boot process, we reset 16, we extended with just our bootloader, and then we try unseal that document, we get back super secret documents. Okay. So I don't know, hopefully this demo, and maybe if you guys do have in your laptop, you have a trusted platform module and you're running Linux, you could run through this demo yourself. I know it's annoying. There's a bunch of other documents that you wouldn't necessarily think are required based on the specific primitives that we have available. But hopefully you saw where these came in, right? I mean, granted, this unseal command was not as simple as this, right? Effectively, we had extend, I think, is implemented just about as simply as it could be, right? Reset, I think, is implemented basically as simply as it could be. It's just you have to specify, obviously, what register, which register you are resetting, which I think makes sense. There's not just one. Again, when extending, you have to specify, okay, well, what register are you extending? And what measurement or what value are you extending it with? So these, I think, are about as simple as they would suggest. For TPM2 seal was a little bit more complicated, right? We had to create a policy. And the policy has to exist inside a specific context, which we called the primary context. And the context has a specific owner. So, that was a bit annoying. And then you call seal, right? Which they just call create. And then unseal was pretty simple. We just had to, load the file that we wanted unsealed, or load the blob or the ciphertext that we wanted unsealed, and then unseal. So I think fairly straightforward how hopefully the demo maps onto these primitives. There's some other commands, but it's those aren't super important. Yeah, cool. And if you guys have any questions, just ask them on the Moodle forum, or you can just email me. Otherwise, I think we can leave it there for today. Remember, you guys are writing your test next week. So yeah, if you do have any questions about the course content so far, that will just cover these first 4 lectures, next week's test. I think make sure you familiarize yourself with the readings and that you're on point with all of those. It will be a written test, not a Moodle test. there will be no programming involved, and you won't have to use TPM or anything. Like you won't use a computer at all. It'll just be writing. Should be about 2 hours at 68 marks. 68 marks, but you should finish a little bit early, hopefully. But yeah, let me know if you guys have any questions. Yeah, cheers, guys. Okay, sorry guys. One more thing I just want to go through. I was just watching the recording back on like 3 times speed, and I just wanted to mention something a little bit specific because I think I think if we were having the lecture in person, this is probably a question that would have come up. And so I was hoping, like when preparing the lecture and stuff, I wasn't thinking about addressing it specifically because but it is an interesting question. So effectively, what we have with the sort of measured boot and the registers, right, is we're building like a tree, right? So we've got, let's say at the base, we have our bootloader or whatever that the ROM knows to run first. Okay, and this could have been a secure boot context where the ROM actually checks some signature or shim or whatever of the bootloader to make sure that it's trusted or whatever. But in our case, for a measured boot, it doesn't really matter. Of course, this is hashed and added onto a PCR, right? So then let's say we boot into Windows 11 or something. Okay, Windows 11. Okay. And then of course Windows 11 will be hashed and again added, and the PCR again will be extended. Okay. And then let's say we ran some other thing like some system process thing, okay, that is important for the running of something, or for some data that we want secured. Again, that's hashed and added to the PCR. And then maybe we had some data that we sealed, right, based on this current value of the PCR, right, on whatever the PCR currently has. Now, of course, because of how the hash works, we couldn't get to this hash, right, this hash value that we ended up at the end here. Let's say this was H0, H1, H2. We couldn't get to this hash if Windows 11 were at all different, right? So like the obvious one is like, let's say our attacker stole our laptop, they booted into Ubuntu, or they modified, or even a modified version of Windows 11 that had their user accounts or something, or whatever, like that had a different password, whatever. And then they launched that system process. And then they tried to unseal our data. Of course, the value of this PCR register, this hash, would not be the same, right? Because Windows 11 was changed, or it was a totally different operating system or whatever. Okay, so this is how we're protected. A very important question about how this functions is, this is cool and everything, but like, let's say the user is doing this, they've got some sealed data on their Windows 11. What happens when they run a system update, right? So like, what if I'm on Windows 11 2.0 or whatever? Okay, geez, I'm just going to say W11. What if we're on Windows 11 2.0, right? This data was sealed using the old version of Windows 11. So how do we handle this? And this was one of the reasons why TPMs and trusted hardware and like this kind of disk encryption is so dangerous, and it actually took Linux very long to get right because of the amount of different things and different vendors and stuff that are running stuff. A lot has to go very right for this update to work. Okay, effectively, what happens is we build the expected register, right? So it's useful us having multiple registers, because you might say like, well, we only have one platform configuration. Why, even when we were doing that demo, right? Like if I do a PCR read over here, we have so many registers. What's the point of all of these registers? We're only running one platform, right? So what would be the point of all of these different registers? The So the answer is, what we can do is like, okay, we know we're upgrading to Windows 11 2.0, right? Right now. So effectively, you know, we're we are going to be building this new tree, right? So like the value of the old PCRs don't change, but we start at a fresh PCR, it's reset. We hash our bootloader like normal. We do step one because our bootloader is not being updated, right? And then we build this PCR here. So now PCR one, let's say our one register has this, our other register has Windows 11 2.0, right, on PCR2, let's say. Then we unseal this data, right, unseal. We unseal this data, get back the data, and then we reseal the data with this new register with PCR2, right, seal with 2 data, okay. Not Perhaps not the best diagram, but hopefully the idea is getting across. And then we can actually delete this and this and this, and we can reset this register. We don't need it anymore. And then we can actually do the update. And once the update is done, we can boot into Windows 11 2.0, and this data has been sealed correctly, and we can decrypt it like normal. Okay. So I just wanted to address this question that I figure someone would have about, well, how do we do an update? If all of the data is sealed against the old platform configuration, if the platform configuration changes, we would lose all of our data. And the answer is this, right? You build the sort of new one, you reseal the data with what the expected PCR after the update will be, then you run the update, and then you can decrypt it. Okay. And that's why it is very useful that we have multiple platform configuration registers, right? Okay, cool. Yeah, I think that covers that.